Hey everyone, welcome back to the Info Engineer. Today, we're diving right into another masterclass explainer. Look, if you're involved in designing, mixing, or pouring concrete, you already know the deal. The decisions you make right at the mix stage literally form the foundation of our built environment. So we're going to move beyond those outdated practices and really embrace modern, high-performance structural design. We're breaking down nominal versus design mixed concrete, looking at why the whole industry is shifting and what it actually means for your next project.
So let me ask you a question. Are you still using Grandma's recipe for your concrete? Now, no disrespect to Grandma, obviously. Her cookies are absolutely legendary. But a traditional baking recipe that just says 1 cup of sugar, 2 cups of flour, it's completely fixed. It's volumetric. It completely ignores the fact that today's flour might behave totally differently than the flour from 50 years ago. And honestly, that is exactly what the traditional 1-2-4 nominal mix approach is like out on the site. Today, we're contrasting that familiar, fixed-volume habit against the lab-tested, pinpoint precision of a master chef. We're talking about the design mix.
Okay, here's our quick roadmap for this explainer. First up, nominal versus design mixes. Second, prescriptive versus performance specs. Third, the risks of the nominal mix. Fourth, economy and structural safety. And finally, we'll wrap up with the water-cement ratio heart.
Let's jump right into Section 1, nominal versus design mixes.
Really, the fundamental difference here boils down to assumption versus guarantee. The nominal mix relies entirely on fixed volumetric proportions. You know the drill, that classic 1-2-4 ratio of cement, sand, and aggregate. It's super easy to use for a quick, small job because pretty much anyone with basic concrete experience can whip it up. But here's the catch. Its compressive strength is purely assumed. You're guessing. On the flip side, the design mix is tailored to perfection. It uses customized proportions figured out through rigorous lab testing. It actually accounts for the specific environmental conditions and the exact material properties of your site to give you a guaranteed strength. If we take a look at the concrete grades based on the IS 456-2000 standards, there is a really clear dividing line. Nominal mixes, they're generally totally fine for your ordinary grade concrete, basically up to M20. We're talking non-critical, lighter projects, pathways, simple boundary walls, that kind of thing. But the very second you step up into standard and high-strength concrete, so M25 and above, the codes essentially demand a design mix. I mean, for load-bearing beams, high-rise columns, heavy structural elements, you just absolutely cannot rely on assumed strength. It's way too risky.
Moving on to Section 2, prescriptive versus performance specs.
To really grasp why the ready-mix industry is evolving so fast right now, we gotta talk about the specs. A nominal mix is born from what we call prescriptive specifications. These are basically old-school rules that tell you exactly what ingredients to use. They'll demand a minimum cement content, or they'll heavily restrict your use of supplementary materials. Basically, they tell you exactly how to make the concrete. But performance specifications, which is what governs design mixes, they don't lock you into specific ingredients. Instead, they focus entirely on the final measured indicators, things like compressive strength, shrinkage, chloride permeability. Performance specs actually give engineers the freedom to innovate and really optimize the mix for whatever the specific structural needs are. Now, what's really fascinating here is how the hard data busts a super persistent industry myth. For decades, those prescriptive specs essentially forced engineers to use high minimum cement contents. But, as concrete expert Dr. Michael Thomas points out, there is a perception that more cement makes better concrete. Instead, it results in an increase in heat and cracking. Right? It's kind of counterintuitive. But those overly prescriptive rules can actually harm the concrete's long-term durability, not to mention drastically inflating its carbon footprint.
All right, Section 3, risks of the nominal mix.
Let's look at how this actually translates to real-world structural failures. Take the incredibly insidious process of chloride-induced corrosion. Say you use a nominal mix in a severe environment, like a coastal area right near the salty air. Well, the assumed density of your cover concrete might end up being completely inadequate. Chlorides will just diffuse right through that highly porous concrete matrix. Eventually, they break down the passive protective layer sitting right around your steel reinforcement. And once that happens, it's game over. The rebar corrodes, it expands, and it literally cracks and spalls the concrete from the inside out. The crucial takeaway here is that the risk profile of a nominal mix and critical elements is just way, way too high. Nominal mixes suffer from over-cementing all the time. That causes a really high heat of hydration, which then leads directly to thermal cracking. Plus, it significantly bumps up the risk of that destructive alkali-silica reaction. Ultimately, relying on some assumed strength for a heavy, load-bearing structure is the massive gamble, and it's one that modern engineering standards simply won't let us take anymore. Which brings us to Section 4, Economy and Structural Safety. 168 kilograms per cubic meter. I mean, that is just a staggering number. That is the exact amount of cement you can save when you switch an M25 mix from a traditional 112 nominal mix over to an optimized design mix. 168 kilograms saved in every single cubic meter. So yeah, while a design mix absolutely requires an upfront investment in lab testing, the material economy on a large project is astronomical. You're saving massive amounts of money on cement, and you're significantly slashing the embodied carbon of the entire project. It's a huge win-win. And the best part? You achieve those massive savings without sacrificing even an ounce of safety. In fact, safety is literally mathematically engineered into the design mix through the formula for target mean strength. As we all know, concrete has inherent variability. So to ensure structural safety, engineers design for target mean strength, that's the FM, that is actually higher than the characteristic strength, FCK. By adding 1.65 times the standard deviation, the design mix statistically guarantees a 95% success rate for structural safety. You aren't guessing anymore. You know exactly what load your building can carry. All right, last up, Section 5, the water-cement ratio heart. As we briefly touched on earlier, it is not the total amount of cement that dictates your strength. It's the ratio of water to cement. This is the absolute heart of the matter, and it was formalized over a century ago, back in 1918, by Duff Abrams. Abrams' law establishes this fundamental inverse relationship between the water-cement ratio and concrete strength. An optimal ratio ensures you get complete hydration of the cement while minimizing any excess water. Because excess water, it just sits there in the mix, and when it finally evaporates, it leaves behind this network of microscopic voids that absolutely cripple your concrete strength. And this inverse relationship is incredibly sensitive out in the field. Just look at the numbers. Moving from a ratio of 0.30 to just 0.40 causes the flexural strength to drop from 8.9 right down to 7.6 megapascals. And by the time you hit a 0.60 ratio, your strength has just plummeted all the way down to 5.4. I mean, literally every single drop of excess water matters here. And that's why performance-based design mixes are so critical. They allow engineers to lock this ratio in perfectly, usually with the help of some modern superplasticizers. But hey, we're not just talking about strength, it's also about long-term durability. As you can see, as the water-cement ratio goes up, permeability and carbonation depth just shoot right through the roof. A high water-cement ratio basically creates a highly porous matrix. It acts exactly like a sponge, just inviting destructive chlorides and carbonation deep into the structure, which completely destroys your durability factor over time. So whether you're an engineering student or a seasoned field professional, how do you actually synthesize all this on the site? Well, here is your practical checklist. First up, look at the project type. Load-bearing structures demand a design mix, period. Second, environmental exposure. If you're dealing with coastal winds or harsh chemicals, you absolutely need a customized, low-permeability design mix. Third is budget. Look, don't be fooled by the lack of initial lab costs for a nominal mix. The long-term material savings of a design mix almost always win out on any larger project. And finally, respect the IS codes. Just avoid nominal mixes above M20 for any reinforced cement concrete work. Ultimately, concrete is the skeleton of our entire infrastructure. As modern construction standards keep rising, relying on assumed strength just isn't going to cut it anymore. So I want to leave you with this question to ponder before your next pour. Will your next mix just fill a space, or is it genuinely designed to carry the future? It's time to embrace the science, optimize those materials, and design for actual performance. Thanks so much for joining me for this masterclass explainer, and as always, keep building smart.